Hello, as Kevin introduced me, my name is Dmitry Belyavskiy. I work in Red Hat. There I maintain OpenSSL and OpenSSH. I also am a member of OpenSSL technical committee. I'm not a true cryptographer. I'm a software developer. I'm not a network engineer, so please consider it when I'm talking about what affects network protocols. My current work is related to post-quantum transition. Red Hat participates in a European grant project, Horizon project named QBIP. And I believe that some parts of that project related to network are also relevant for the audience. Okay, so I believe that you recognize these people, Alice and Bob. They were invited by Ron Rivers to demonstrate how important cryptography is for protecting the communication, and now they are probably in trouble because of post-quantum threats. So let's begin with some clarification. There are two different terms that shouldn't be mixed. The term quantum cryptography is dedicated for cryptography based on quantum mechanics, such as, for example, quantum K distribution, some random name generation, and so on and so forth. I will not cover this topic in my presentation. I don't understand in this area anything at all. But post-quantum cryptography is a completely different beast. It's also known as quantum-resistant cryptography or quantum-safe cryptography. And it's a cryptography that will be safe for using when quantum computers happen. Why do we need a transition at all? There are quantum threats. In the middle of 1990s, the scientists Shor proved that quantum computers, well, you can use something like it's magic, but usually it's named quantum computers, will break traditional cryptography. Mostly, we are speaking about so-called asymmetric cryptography. So those who are familiar understand that it's classical RSA algorithms, it's elliptic curve or digital signature or classical digital signature, and Diffie-Hellman key exchange based on the same math. They are used in the most protocol, especially at the handshake phase. And if they are broken, it significantly undermines the security of communication in the network. Well, again, quantum computers are currently sort of magic, and they are not here and hardly will happen here tomorrow. But post-quantum transition is near. All the governments are taking measures in these directions, and currently it's expected that post-quantum algorithms will become mandatory at some moment around 2030. In different countries, there are different forecasts. The history of introducing post-quantum protocols in the standard begins really in 2016 with the NIST contest. There were 70 participation in the first round. Then the amount of the candidates was reduced, and in 2022 we got first 4 algorithms suitable for future standardization. It has taken almost 2 years since that moment, and we got 1 algorithm suitable for K establishment, and 2 algorithms for signature, and 1 more algorithm for signature is still in queue. It will hopefully be standardized till the end of the year. And it's still ongoing process because, well, we can't be sure that new algorithms produce real safety. There were 4 algorithms selected for round 4, which of them happened to be broken completely without any quantum computers. There is a new contest for additional signature algorithms, 14 algorithms. So stay tuned. Again, let me briefly enumerate what are the standard bodies and so major players. Yeah? The first is NIST, as I mentioned before, that standardized two algorithms for signature. MLDSA that is expected to be used in TLS, in X509 certificates, and so on and so forth. And SLHDSA, which is intended to use for signing, for example, firmware. And they also standardized the algorithms MLChem for key establishment. Now, when all these algorithms are standardized, it's time for ETF to make the final standards of using it in various protocols. The process began also several years ago, but now when we have final standards, we can better understand what to do. And also one more player is Oasis Group, which, for example, defines the PXS 11 specification, and it means hardware support and interfaces for working with hardware. As I mentioned before, I'm not a mathematician, yeah, so feel free to download my presentation and click the links. This is the series of blog posts at our site that explain mathematics at the level necessary to understand what it is for and how it's used. And now let's switch to the challenges. One of the main challenges is fundamental. We are going to build a secure system relying on doubtfully secure components. We can't trust classical algorithms anymore because, as we definitely know, that quantum computers, if they ever happen, will break them. And at the same time, we still cannot trust new algorithms. As I mentioned before, one of them was completely broken. And they're just investigated for too short time to be sure enough that it will not be, that they will not be broken tomorrow. It means that as a temporary solution, we have so-called hybrid approach when we combine K materials or signature got using the traditional cryptography. Got by quantum cryptography. It ensures that while one of the components provides some level of security, we have the guarantee that cryptography is not broken. But that's not the only challenge. The other challenge is related to the parameters of the new algorithms. First, and what will affect the network protocols significantly is that new algorithms all have big keys, signatures sizes. If we rely on, say, 128 bits of security, we, for RSA key, which is the biggest key for that level of security, we have less than 400 bytes of the key and signature, each of them. But for MLDSA, which is expected to have the same level of security, we have significantly larger keys. Yeah, so we get +1 kilobyte on the key and +2 kilobytes on the signature. Next one, the performance of the algorithms. Cloudflare showed the measurements that, for example, hybrid key exchange is fast enough. Yes, it's fast enough. But on the other hand, Google introducing the MLChem support don't introduce it in mobile browser because of performance issues. It's not. So, and it's too early to see whether the performance will be improved. Of course, it will be. But now implementations are imperfect and in general slower than for traditional crypto. There, of course, will be compatibility problems related to middle boxes, related to errors in implementation, because, well, classical algorithms have been implemented for decades, and the post-quantum algorithms are relatively freshly implemented. But as I mentioned before, we also get network-specific problems. So we have two use cases for asymmetric crypto: DSA, digital signature, and key establishment mechanism, KEM. DSA is an answer to a question: did you connect to a proper peer? Was the email of proper, and does your fresh firmware update come from a trusted source? Key establishment is using for elaborating the symmetric keys to protect the overall communication. So it means that these components have different threat model and different countermeasures. For DSA, the threat model is that an attacker would restore a private key by the public one and impersonate the site. After that, they become able to mount the middle attack and extract secrets in real time. Control measures for this attack require new hardware, new trusted routes, shipping these trusted routes to each and every device, and new end user certificates, new domain certificates, and so on and so forth. But this attack is real time and is not possible without real quantum computers. Key establishment has a significantly different threat model, and it's more dangerous because that attackers can collect data now. Then they are able to restore symmetrical keys when these quantum computers are established, and if your secrets are still secrets, they will be revealed. But luckily, the countermeasures are completely on software layer. We expect that it will be easier to fix it. For example, speaking on TLS, there are widely set experiments based on pre-standard version, Kyber, and Kyber-based hybrid. They are available in Google Chrome, they are available in Firefox, they are provided in Cloudflare, and currently we see the process that this key exchange is moving to the standard versions. Google already uses MLChem-based hybrid, for example, on YouTube. So, let's jump to network problems. We have certificates. We have not usually we have not a certificate, but certificate chain. And comparing to RSA, we get much bigger size of this certificate chains, because for each real world certificate has one public key plus 1 kilobyte, signature of the issuer plus 2 kilobyte, and at least if we are speaking about web, at least 2 certificates from the certificate transparency log plus 4 more kilobytes. So it means that chain turns into 22 kilobytes from 3-4 kilobytes. Also, network protocols have request response limitations. It's standard in the QUIC. Don't know how widely is it implemented, I mean this limitation. And it's a recommendation in DTLS. So it should be investigated and measured. The other traditional problem is related to TCP slow start. TCP initial send window is about 10 MSS, so it's something like 12 kilobytes. And as you see, 22 certificate chain does not fit this 12 kilobytes. So you can investigate larger MSS. You can rely on certificate compression, which slightly helps. You can reinvent the X509 standard, which is proposed by Google, but it's a problem you will meet. Again, for UDP-based protocol, there also will be some congestion issues. And there were worse investigation and measuring. Last example I would like to cover is DNSSEC. It's my beloved protocols, all problems in one. So it's suitable for amplification because small requests cause huge responses. The RR6 hardly fit one packet now and will definitely not fit one packet on moving post-quantum stuff. There is a proposal RRF, named RRF, to split RR records and deal with them at application level. And I know that after the launch, there will be a great presentation about DNS field experiments. I strongly recommend all the audience to listen to it. I have listened to the previous version that was done at the IETF. If you want to make your post-quantum experiments, I will briefly talk what we have in Fedora. We use the libocase library from the Open Quantum Safe project. It provides low-level implementation of all the alive post-quantum algorithms, not only standardized. We ship OpenSSL provider. It's a plugin for OpenSSL that is suitable for using post-quantum crypto with OpenSSL. We also have implemented a post-quantum container as a part of the Qubit project I mentioned earlier. So feel free to download and use for experiments. And of course, we continue the upstream work with the important libraries for our distribution, OpenSSL, NSS, GNU-TLS. This slide illustrates what's currently in the scope of the post-quantum transition for operation system. Yeah, we will provide post-quantum algorithms in libraries. Cryptopolis is a feature of many distributions that establish system-wide defaults for crypto algorithms. I think it's a quite useful feature. Applications are out of scope of the transition, but I will speak about them later. And kernel stuff and remote attestation are currently out of scope, but it's inevitable that we will have to add post-quantum support to there to avoid tampering the boot process. Which algorithm to choose? Well, the answer is luckily simple for us. There are basically only algorithms chosen by NIST, and European countries follow NIST recommendations. I know. There are still deployed Kyber-based hybrids for K-Exchange, but they are in the process being replaced by MLCam and almost replaced. We expect incompatibilities between implementations just because there are several of them, and I believe that they have some bugs, and those bugs are in different places. I briefly want to mention OpenSSH that has a non-standard algorithms NTRU for several years, and they have recently implemented MLCam algorithms, and we have a freshly establishing IETF process for SSH protocol standardization. So we believe that they will also rely on standard. What can you do for post-quantum transition? Yeah, test your networks. Establish your fake CA, generate MLDSA keys, measure what happens. You will be surprised how much problems you will find, I think. For a case of applications, you will have to find which limitations are hard-coded. Again, you will be surprised how many applications think that there is no crypto beyond RSA. Yeah, when I was asked, do you enforce using new API of OpenSSL? After a counter question, I understood that they call new the API that is basically 15 years old. Please use this new API of OpenSSL. And please work with IETF, with other standard bodies. Choose your beloved group, choose your beloved protocol, and make sure that they are post-quantum ready. Especially, I would recommend to see whether RPKI still recommends RSA and nothing beyond RSA. But I am pretty sure that there are much more network protocols that are not currently ready for post-quantum transition. And this is basically the final slide, which contains the links to the papers and the publications I strongly recommend to read. Post-quantum cryptography for engineers is a nice IETF draft, which soon is going to become a standard, which explains the basic terminology, threat model, and so on and so forth. There is also a nice paper, Do We Need to Change Some Things, which basically have inspired me to make this presentation. There is an IETF draft for post-quantum DNSSEC research agenda. And the last link is a link to the previous version of the presentation of field measurements on post-quantum DNSSEC. But in the next version of my presentation, I will replace it with the link to the presentation that will happen after the lunch. Thank you very much. Feel free to ask questions.